Now we move on to our next cipher. It's called the Decimation Cipher. First thing we're going to do is look back at the shift cipher, which we learned a few ciphers ago. We're going to change the rules of the shift cipher slightly, changing addition to multiplication, and that will get us the decimation cipher. Then we're going to define the multiplicative inverse of a number modulo some integer n, and then we're going to use that to find a way to decrypt the decimation cipher. And finally, we're going to demonstrate some difficulties in defining the decimation cipher. So let's recall what the shift cipher does. First thing you do is you turn each letter into a number between 0 and 25. For encryption, we add the key to the number version of the plain text, and then we compute that result mod 26. And then for decryption, what we do is we subtract that same key from the number version of the ciphertext. So we add the key for encryption, we subtract the key for decryption. For the decimation cipher, it's going to look almost identical. We're going to turn each letter into a number between 0 and 25, just like before. For encryption, we are going to multiply the key to the number version of the plain text, and then we're going to compute that result mod 26 before we convert that back into a letter. And for decryption, well, we divide by the key, I guess. Let's see how that would work. Okay, so let's suppose we're using a decimation cipher with key 3. Okay, so if we encrypt D, here's what's going to happen. We're going to take D, we're going to convert it to the number 3, then we're going to multiply 3 by the key 3. The first 3 is the D number, the second 3 is the key. That gives us 9, and we look at 9 and that corresponds to the letter J. So we'll encrypt the plain text D with the ciphertext J. Now if we were trying to encrypt T, that would be, basically the same process. We're going to take T, that's 19 when you take the number version of it. We're going to multiply that by 3 to give us 57. We have to mod that out by 26 because 57 is bigger than 26. That'll give us 5, which is the letter F. So let's see how we're going to encrypt that. So if we're going to decrypt J, by the process we outlined above, we should get back to the letter D. And in fact, we do, right? J is the number 9, and if we multiply by 3 to get J, we should divide by 3 to get back to the plain text. So that gives us 3, which is the letter D, and that works out great. What am I getting so worried about with this division stuff? Well, let's see what happens when we try to decrypt F. Remember, F came from the plain text T, so when we decrypt it, we should get T. So we take F, we look at its number, it's the number 5, we divide by 3? Yeah, that doesn't give us a whole number, right? It's supposed to give us T, which is 19. Of course, 5 divided by 3 is at 19. So something fishy is going on here. So here's what our fundamental question is. What does it mean to divide by 3 when you're doing something mod 26? Because what really happened was that when we multiplied 19 by 3 to encrypt T, we had to mod out by 26, and that's going to screw up some of our arithmetic. All right, so we asked the question, what in general do we mean by dividing by 3? Because we're going to have to look at that in a different way. Well, one way of looking at that is multiplication by 1/3. So division is really a special kind of multiplication. And then, of course, that begs the question, well, what's the significance of 1/3? Well, 1/3 is the number we multiply by 3 to get 1. If I multiply 3 times 1/3, that gets 1. And if you want to look at that algebraically, it's the solution to the equation 3 times x equals 1. So division by a number is the same as multiplication by its multiplicative inverse. And this allows us to get around the weirdness of division by thinking of it as multiplication, which is less weird. One thing I want you to remember is that 0 can't have a multiplicative inverse. There's nothing you can multiply by 0 to give you 1, no matter how hard you try. And then this leads us to the definition of what it means to be a multiplicative inverse modulo n. So let a and n be integers such that a mod n is not equal to 0. And again, 0 is important because from that recall, 0 can't have a multiplicative inverse. We say that some number b is a multiplicative inverse of a mod n if a times b mod n is equal to 1. So in other words, when we multiply a times b, we get 1. Well, maybe we don't get exactly 1, but we get 1 when we mod out by n, which is really what we're looking for in that decimation cipher. So if we want to think about a multiplicative inverse for 3, well, let's see. You have to mess around and try some different things to multiply by 3. But if one thing you'll hopefully latch onto is that 9 times 3 is 27, which doesn't look great, but remember, 27 mod 3 is 1, which means that 9 times 3 is mod 26 is equal to 1, and that says that 9 is the multiplicative inverse for 3 mod 26. So if we want to divide by 3 mod 26, what we really want to do is multiply by 9. Kind of weird, but that's how it goes. So here's our key is 3. Our plain text is howdy. And what we do first is, if we want to encrypt this, right, we want to convert each of the letters into a number. And 7, 14, 22, 3, and 24. Then we multiply by 3 because that's our key. We get 21, 42, 66, 9, and 72. Now, obviously, we can't put those in letter form yet because we have to mod out some of those by 26. The 21 stays, but the 42 turns into 16, the 66 turns into 14, and the 72 turns into 20, and then those can be converted into letters V, Q, O, J, U. Now let's look what happens when we try to take that ciphertext V, Q, O, J, U and decrypt it using the multiplicative inverse. Hopefully we'll get back to howdy. If not, then this is a bad road that we've gone down. So first thing we're going to do is convert the ciphertext into numbers. Then remember, our multiplicative inverse of 3 is 9. So we're going to multiply, and the reason, again, is because 9 times 3 mod 26 is equal to 1. So we're going to use that to multiply each of those numbers in the ciphertext by 9. So we get all these numbers, 189, 144, 126, 81, 180, and then we mod that out by 26, and we get the numbers 7, 14, 22, and 3, and 24. Again, all we're doing here is dividing each of those numbers by 26 and looking for the remainder. And if those numbers look familiar, they're exactly the numbers we got from howdy. So when we decrypt it using that multiplication by 9, it actually does get it back to howdy, just as we expected it to, right? Multiplying by 9 is the same as dividing by 3 when you're in mod 26 world. All right, so here's a summary just of the decimation cipher, just so you understand what's going on. For encryption, the first thing you do is convert the letters to numbers. You multiply the numbers by the key. You compute the resulting numbers mod 26. In other words, you take them mod 26. And then you convert them back into letters, and that's your ciphertext. For decryption, you're going to first convert the letters to numbers again. Your decryption key is going to be the multiplicative inverse of the encryption key, mod 26. So you take your encryption key that's from encryption, you find its inverse, multiplicative inverse, mod 26. That's going to be your decryption key. You're going to multiply each of those numbers in the ciphertext by your decryption key, and then compute the resulting numbers, mod 26, and then finally convert those back to letters, and that takes you back to the plain text. So that was great, but here's an issue that can come up if we're not being too careful. So what if someone tried to use the decimation cipher, but with a key of 4? Now 4 looks perfectly harmless, but it turns out 4 is a troublesome little key. So first thing I want to do is I want to search for a multiplicative inverse. Now we don't have a nice way of finding multiplicative inverses in general yet. We will have an algorithm that does that later, but right now what we have to do is we have to check out all the numbers and see if they work. So that top row is, I say inverse because I'm wondering if they're inverses, and if you're worried that it only goes up to 11, don't worry. I only did that because I ran out of space. We'll have to do the other ones in different rows. So I'm just going to check 1 through 11 now, see if any of those is a multiplicative inverse for 4. So what we're going to do is we're going to multiply each of them by 4 and see if we get 1 mod 26. So I mean, these are all just multiples of 4, 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44, just like in those old Schoolhouse Rock videos, right? And now what we're going to do, which is very different from Schoolhouse Rock, is we're going to look at those numbers mod 26. So once we get to 28, we have to start modding, and we got a lot of numbers, but sadly we don't get 1. All right, so no inverses in 1 through 11. Let's try 12 through 21, right? Again, we're going to multiply by 4, see what those are. We're going to mod out by 26, and we got 0. That was fun, but that's it. I mean, no ones. And in fact, there's a weird, eerie pattern seems to go. I'll hold back until I get to the end. So the last 4 that we check is 23 through 25. Again, we multiply those by 4. We notice, oh no, there are no ones in there when we mod out by 26. And so I was saying there was something eerie going on, and the reason that's true is if you look at all the numbers mod 26, not only do we never get 1, we never get an odd number in there, right? They're all multiples of 2. They're all even numbers, which is weird, right? No odd numbers? Yeah, that's the way it goes. But we didn't get 1. But what that tells us is there's no multiplicative inverse for 4. There's no number that we can multiply by 4 to give us 1 mod 26. So that is troublesome. So that tells us that, I mean, the key of having a key of 4 is going to give us trouble. So it turns out it's even worse than that, right? It's not just that we have this key and we can't find a multiplicative inverse, so we don't have a good way of finding out how to decrypt stuff. The fact is, it's impossible to decrypt some things. So for instance, here, let me give you an example. So let's say our key is 4, and let's say I want to encrypt the letter B. So I look at B, I convert it to a number, I multiply that number by 4, and that gives me the letter E. So far, perfectly innocent. However, what if I look around and decide to encrypt the letter O? Well, same process, right? Look for the number for O, that's 14. Multiply 14 by 4 to get 56. Mod out by 26, and I get 4. And that gives me the letter E again. And that's trouble, because now I have 2 different letters that get encrypted in exactly the same way. And that tells us, since E is the ciphertext for both B and O, that means it's impossible to decrypt E. So not only can we not find a multiplicative inverse to help us figure out how to decrypt our messages, it's actually impossible to decrypt our messages because we have certain letters that cannot be decrypted at all because it has too many choices. And in fact, I'll spoil the surprise. Every single letter of ciphertext is completely ambiguous in terms of how it can be decrypted. None of them can be decrypted uniquely. So that's trouble. All right, so now that I left you on that unsettling note, why don't you go ahead and try working on the decimation cipher exercises on the PDF file included with this video.